Hello, everyone, January 18th. Alright, so we didn't solve yesterday's problem. So I have to do it today, early in the morning. But we read the solution and we knew that the problem can be solved by turning it into a Dijkstra. So I solved using Dijkstra and coded it up in C++. It was alright. It was not that bad and pretty slow. And then I was reading the tutorial and I saw this. Where is it? 0, 1. Yeah, I completely forgot about the 0, 1. So I think 0, 1 is pretty much the same as the extra, except you don't use a priority queue to order. So let's see what you use. It's using a deck. So you have the minimum cost, you have the deck, you have this, and you have minimum cost. So decks you pop in the front, and then you try 4 directions. You get a cost. You do direction this way. That's fine. If position is a valid, then we find a better path, right? So is valid, and this is smaller. Okay. Add to back. Add to front. Now I get it. You look great. Sorry. I love it when my wife asks, where's my teeth? That's the trick. You put at the back. If you have a cost, you put at the front if a cost is 0. Okay, so that is, I think that's exactly what we need. So we're gonna write another solution for this, just to, honor the so this one we are call it since the it's the same, like same as solution 2. However, since the cost of each edge is at most 1, we can use 0, 1. 0, 1, what's it called? BFS, which essentially is Dijkstra, right? Dijkstra without using the priority queue, because there is only one possibility to increase the cost at each step, right? If the cost is 0, we put the next node to the left of the queue, otherwise right. So this is the same, this is the same, this is the same. This is not a priority queue. Instead, this is going to be a deck. Of course, we also don't need a cost for this. Oh. So this is going to be a deck, and a deck of this. This should be, okay, call it Q. Okay, so this should be Q dot, I'm not sure. Huh. push back. Okay, push back this. This is a fine, so this should be while q, right? And then we have q dot, doesn't have top. Pop front. Okay. Front. Right, and then q dot pop front. This is the same, this is the same, this is the same. If it's smaller, actually it's not really smaller. I think it's just yes. Alright, let's get back to it. So we got a new cost. So here is the interesting part. So the other one is if the cost is smaller than the original, then we will push it, but we don't push it, right? It depends on yeah, because the cost is either 0 or it is 1. So basically we'll say if the new cost is equal to the cost, which means this is 0, then we put it in the front. So we just say if new cost is equal to cost, then we do q dot push front ninj, okay? Else we say q dot push back ninj. Okay, so this is the so-called 1, 0, 1 BFS. Oh, of course. There's no cost. My bad. There's no cost here. If there's no cost, if there's no cost. Okay, this is something different. I guess we just don't do this. And we'll say costs ij here. Oh, so it should just be weight W. I see. It's a BFS W. So this doesn't make any sense, right? This is the weight, and we can say costs ij plus weight, right? And this should be costs ij plus weight, and weight is equal to 0, push the front. Okay, so I'll make some changes here. Okay, that was a bug. Okay, this one might be right. Submit it. Similarly slow. So this is supposed to be OMN. Okay, that's OMN. I think the only better is the DFS and BFS together. I'll leave it be. This will be the last solution I want to work with on this one. I mean, the key to this problem is just, you know, we need to convert it into a graph. Then you will have it. Right? Okay, so call it done. That's today's problem. Trapping rainwater. Oh, it's a 3D now. Ha. Oh boy. Do you still remember the old problem? Yes I do. Old one is a 2D problem, I think. M by N, integer matrix, height map representing the height of each unit cell in a 2D elevated map. Return the volume that I can trap. Wow. I think trapping rainwater was one of the iconic ones. And the previous one is a 2D problem, so you just have something like this, right? And they ask you what's the trapping. And I believe this is like a monotonic array type of thing. I need to recall how this one is done. Um, I think it's monotonic decreasing, right? So you keep adding, and when you add something big, you will pop. And when you pop, you will add. So you know the front. The front is the top, the highest point, right? And then the amount of water you can hold so far is dependent on the lower point of these two, right? So in this point, when you pop this, you can hold like this amount of water. You can hold this amount of water. And then when this one is pop, it's nothing in between. I forgot how the rain trapping is done. Hold on, let me think. Trap water. Go down, go down. I also remember you have to. Yeah, no, it's the height difference. It's the height difference, and you need to know the index in between because all this area will be filled with water. So you get. So when you pop something, hold on, hold on, hold on, hold on. So when this one comes in, what I want to know is how much water can be held. Like above this. I remember it's the very first one, trapping rainwater. Yes, this one. Right, trapping rainwater. Uh, let's not read it for now. So when you're coming in, you know what this is. So basically, this is zero, right? You push zero in, and then you have 0, 1, 1 pop 0, right? You push a 0, so have a 1, 0. And then 2 comes in. So 2 will pop 0. So when you pop 0, you need to know what it will hold. Yes, so instead of popping it, you check the one in front so you know how much this one can hold, right? When you pop this, you know how much above it, right? So you have a previous wall, you have the current wall, and then you have a new wall coming in. So what you want to know is from this wall to this wall, above it, how much water this is. So in this case, you pop this and then you compare to the one to the left, right? And to the left, so the difference is 1. So these two differences 1. So this you have 1, right? You got 1. And you pop it, and then you have a 1, but this one doesn't have anything in the left to help, so you just pop it. So now we have 2, right? And then we have 1, then we have 0, then we have 1 again, so this one plus 1, because this one pop, right? Plus 1. And that's equal. What do you do with equal? You don't. what do? You need to keep this because this position is important, right? So you found this, you keep popping, and then you put this one in, right? You put this one in. So now we have 2 1 1 2 1 1. The next 3 comes in, right? 3 comes in, and you look to the left. Huh. So when you pop this, you know what? No, I think this one should be popped. But you get no water, right? It should be popped. Now the 3 comes in. Should be the taller of these two. Right, should be the taller of these two. So 3 comes in. So we need to pop this. So we compare the front and this. This one is shorter, so we do this with 1. And this is this one, so I get 1. So pop. Now we have a 2. So now we're popping this one basically, right? And now we need to pop this 2. See, that's the thing. Oh, we should have both. So when popping this, we compare, so that's a 1. Now we pop in this, right? Now we compare as a 1 as well. But this has 1, 2, 3. So this will be plus 3, right? We have plus 3. Oh, we are not really plus 3 because this one already have it. So I get this, and this comes in, and if I pop, then we'll have, oh, when this one popped. Yeah, but I cannot pop this, right? Yeah, so I add this. So I add this part. Then I need to pop this. Because it's from this towards the end. So you cannot add this. Yeah, you should not add this. If it's the same, you don't add it. If it's smaller, you add it. But if I have the same, you just skip it. Now this comes, and I'll pop this, right? And then I compare this and this. This one's smaller, so it'll be 1 times the difference between them. So we add a bunch, right? And I want to pop this. I cannot, so I do this. Now I go down, go up. And we do this to the left, right? And then we got this. So we have another plus 1. Okay, I think this is one method. Another method, if I remember right, is I think 2 pointers. So we have a pointer pointing to the left and another pointer to the right. I forgot how this one's doing. The 2 pointer one. I forgot what the 2 pointer one was. Let's see. I shall have a wait, I cannot see my solution? Oh, the solution's here. So monotone decreasing array, yes. So I have a stack. If it's larger than this, and height I is larger than this, yeah. So we pop this one up, compute amount of water between I and then stack. Yeah, so we pop it, and we'll compute. So we get a minimum height, yes, between these, minus height j, that's the amount that you can get, and then you'll times the difference. And eventually you need to add it. Ooh, this is something I don't understand. This one adds this I. So if we equal, I will still add it. When we pop, oh, you compare to the previous. You compare to the previous, and the previous height will be 0. Ah, okay, that makes sense. Got it. How about this one? So keep track of the left max and the right max. When left max is smaller or equal to the right max, and if height low is smaller than left max, then it is guaranteed that the amount of space above height low but below left max can be collected as rain. We keep moving low to the right until left max is larger than right max. What the hell was I saying? So we keep the left max and the right max. Okay. When left max, the maximum on the left is smaller equal to the right. And so we have the left max. And if it's smaller equal to the right, and the current left height is smaller than left max, then it's guaranteed that the amount of space above height low but below left max can be collected as rain. We keep moving low to the right until left max is larger than right max. So if left max is smaller than right max, and whenever we hit is smaller than we can collect, because it's dependent, it's always dependent by the left max. But whenever we have the left max become larger than right max, then we need to work from right to the left, because now holding water is dependent on the right. Okay, so we have low and high. So left max smaller than right max. If this, we'll add this. Otherwise, we update. Okay. Yep. I know this one. All right, so we basically have two, right? We have two solutions. So we have two solutions for this problem. Now we come back to this 3D. So 3D is basically, we have each row, we can collect water, and each column, we can collect water as well. I actually prefer the monotonic array solution. I think I'll implement it like monotonic array. So the problem now is if we go row by row, we'll have some capacity to collect water, right? Like in this case, we can see for this row, like this cell should be able to collect water. If you look like, actually, is that a row or column? A row, right? This is a row. This is a height, right? So this is a row, the bottom row. 2, 3, 3, 2, 3, 1, that one, right? So that one, this 3, 2, 3, 3, 2, 3, this shall be able to hold water. So I can compute this and say, okay, at this position you should hold water. But if you look at this column, which give us, I think it's 2, 3, 2, right? So this is, actually no, 1, 2, 3, 1. Yeah, 1, 3, 2. 1, 3, 2. So 1, 3, 2, then it should not hold water. How do you reconcile this? Gosh. So for a row, you get what you can. You can mark it. Holy. Dude. I think we need to use the other method. Because the other method I can tell at, like, if we go row by row, right? If we go row by row at each index, how much water can be collected, right? So if we go row by row, we have 1, 4, 3, 1, 3, 2. So if we go row by row, we'll say start with 1 and 2, right? That's the starting point. We have a left max, we have the right max. So right max is bigger. Right. Right is bigger, so we go to right. So now we have 3. 3 is bigger, so we keep on 3 is bigger, we keep on the right. Now we have 1. So 2, 3, 1. No, left is bigger. My bad. Left is bigger. No, left is 1. Right is 2. So whichever side is bigger will move. Right? And then we have whichever side is bigger. No, we move it on the other side. Whichever side is bigger. So this side is bigger. So we move on this side. So we move it on here. And now this is bigger. So now we move down here. Right, because this side is bigger. Left max is bigger. Then we move here. Then we compare it to the right max is 0. So we don't really add anything. So we move down here. And then we move down here. Its value is 3. It's still smaller. And then compared to the max, so we basically reset the max to 3, but we still move down here. So this will be plus 2. Right? Basically behind it would be plus 2. Right? And then we move down here. So this one shall be plus 1. Right? So that's kind of the first row we done. Now we go to the second row. 3, 2, 1, 3, 2, 4. Again, so we move here. Here this should be plus 1. This should be plus 2. This should be plus 1. Right? Plus 1, plus 2, and plus 1. Last one. 2, 3, 3, 2, 3, 1. So I move here. Now move here. Now these two are equal, but doesn't matter. We just pick a side. We say equal, we'll pick this side. Right? Still equal. It's fine. Pick this side, so it'll be plus 1. So this is going rows, right? We have this. Now we need to go in columns. Okay? Go columns. Go this side. coming here, update, so this is 0. Here, 4 and 3, so we go this side, and plus 2. Oh, you plus the minimum, right? So here, I should be plus 1. So plus 1, so this is good. This 3, 3, doesn't matter, I can move here, and shall be plus, so basically on this side, you also need to, this one is plus 0. So this one just canceled out. And here, this will be plus 2, so this one's good. And this will be plus 0. Right? Essentially on the edge will always be 0. Well, set those to 0 first, and then, actually no, we just set it and then we put it in there, right? And we set it to 0. And then we choose which side is bigger, so we move the other side. We choose which side is bigger, then we move the other side. Okay, I need to read the implementation again. I was not very certain about how I went through this. Okay. Let's see one more time. Right, so we have low and high, we have, If left max smaller, oh, I compared it directly. Compare it directly, and if it's smaller, I'll set it. Otherwise, I will reset. Okay, I just need a reset. So they are at that position, right? So we will reset on one side, but then they will come out, right? They will come out. They'll come out, which means on the other side I will not do any operation. That's not good. So I need at the beginning to set the low and high, right? I'll set low and high, and then I'll run this algorithm, right? I'll say low and high, because it's this, so it will move left to small and right, so I'll move the left. So I do this, the low, because I already set to 0, and then it's going to be low plus plus, right? Here, low and high, so low we set to 0, low plus plus, and this become higher, so I'll move down here. Oh, maybe I don't need to, because eventually we are here now. This one is bigger than this one, right? This one is bigger than this one, therefore we are switching here, so this will cancel, right? This one will cancel, and then this one will move here, and then low is would be equal to high. Low equal to, I don't think low should be equal to high. I think low smaller than high is good enough, because you're meeting at the same thing. Like if low is equal to high, that will definitely be this, because we'll update the low and high, and it'll be equal. We just do this. Yeah, I think it should be just smaller. Maybe I don't need to do extra, because as if you think about it, one side will move, right? One side will move until it moves to the other point. Until it moves to the other point. Like worst case scenario, one side just moves through everything, and I hit the other point, and then the other one needs to go, right? And the other one needs to go because now left max is larger than, so we can move. Now we move on here, and then it will cancel this, and then this is the same, so this is equal to here, right? Left max is smaller than right max, so we move left, so this was set to 0, move left here, and then this is smaller than this, so at +1, and then we move here. Now they're equal, so we'll move right. I think this is good. Yep, we should do something like this. So we basically do it 2 times, right? We do it 2 times. Now we have just a simple problem on this, which is I want to write a helper function which can help me do this. So I just need to run it twice. How do I write a helper function that can guide me if I want to go row or if I want to go column? Is it possible to write one function to do both? Well, low and high, but then the INJ is an issue. I think for our purpose, it's okay to write it twice. I think I'll write it twice. I'll write it twice. Alright, so basically I need height map dot size, height map 0 dot size. Okay, and then we need a vector of vector. This is water. M N, and we need to hold this we need to get the minimum, right? We're gonna get minimum, but we need a value that's big enough. All right, what value are you thinking about? Do we have like int max, something like that? I have no idea. No, just int max. Oh yeah, we do have int max. Alright, so everybody is set to int max initially. These are the water they can hold. So we go horizontal first. Horizontal and fill water using the 2-pointer method. Okay, so we have low is 0, high is n-1. Okay, and then row by row, right? 4 int I, 0I smaller than n, I plus plus. You know what? I feel more comfortable doing this. Right, now we have the rows, and we also have left max, say height map I, low, and right max, height map I, high. Okay, so while low is smaller equal to high, right, while low is smaller equal to high, I say if left max is smaller or equal to right max, we'll move left max, we'll move low, and we just compare. We say if height map I low is smaller, right? If that is smaller than left max, I guess it's smaller or equal to, which is fine. I guess it doesn't really matter, right? Then we say we'll basically we'll set the value. We say water I low at this position shall equal to left max minus height map I low, right? We say at this position we can hold this amount of water, else if we can't, then left max shall equal to height I low. Once we're done, low will move forward. Of course we'll have else, the exact same thing will be height map I high, right? If it's equal to right max, we say water I high shall equal to right max minus height map I high. Else will be right max equal to height I high. After we do all this, high need to minus minus. Alright, so that is the first part. We go horizontal to fill the water, right, to fill the water, and then go vertical and update the water. Right. We can only take the min of the two directions, right? The two directions. The main water, right? The min water of the two directions. So this one will be for int j equal to 0. J smaller than, oh my goodness, I think I write something wrong. That is m, right? So this is j smaller than n, j plus plus, right? So again, low shall be 0, high shall be m minus 1, okay? And int, you want to call it left or on top max, okay? Height map, so this is going to be low j, bottom max, top and bottom, height map, high and j, right? But the concept is exactly the same. Low smaller equal to high. If top max is smaller equal to bottom max, okay, if that's the case, then we move top, okay? We move, you know what, maybe we should say TO and a BO, but it's okay. We go low and high, that's fine, right? Low and high. So if, right, if height map low j is smaller or equal to top max, okay, if that's the case, now here is interesting. Water low j shall equal to std maximum water low j t max minus height map low j, okay? Else we'll reset t max equal to height map low j, okay? Now else if height map something is not right. Okay. Yep. Else, if height map, use of undeclared identifier high, subscript pointer type. Wait a second, what? Alright, I think I messed up some stuff. If else. No, I don't think so. Oh shoot, this is not height, this is a height map. Oh wait, hold a second, what are you doing? Yes, this is a height map. I don't know why I just do height. Should be height map. Height map. There you go. Use of undeclared identifier. Oh, I see. This should be this. There we go. Now we're good. Alright, so this should be high j, small equal to bottom max, then water high j shall equal to std maximum, dude, minimum. Holy crap, minimum. Water high j, right, and this is bottom max minus height map high j. Okay, else then bottom max will reset to high j. Forgot something. I forgot here low need to plus plus, and here high need to minus minus. Alright, let's see. Looks to be okay, and then they all just get a minimum, right? And then once I'm done, right, I will set alright, something is still not right. Yeah, I think something is still not right. Hold a second. So this is good. This is good. I think we're missing one. There we go. Yeah, we're missing one. And here I'll set rest equal to 0, and we have to go through the whole water. So for int I, here we're gonna do this auto row of water, right? And for auto w r of row, if r is smaller than int max, rest plus equal to r, and we'll return rest. Oh boy, that's a lot of coding. Alright, let's see. I'm not even sure if it compiles. Dude, it does compile. Alright, so we can do this here. This is a 407. I had to revisit problem. Okay, what was that problem? (42), right? I have to revisit problem 42 because I was not very sure of the solution. Right? I knew it can be solved by monotonic decreasing array, which is the standard solution. However, for the current problem, the two-pointer solution seems to be more appropriate. I need a little primer, right, from my previous solution in problem 42 to recall the essence of the two-pointer solution. Now for the current problem, right, we can run the two-pointer solution for each row. However, and record the amount of water trapped above each height. However, the water recorded for this run is not guaranteed. We need to do a second run vertically for each column. For each column, and update the amount of water that can be held, right? That can be held above each cell. We take the minimum of the amount of water above a cell for the minimum between the horizontal and vertical run. Finally, we sum up all the water, and that is our answer. Runtime is mn. Okay. No wonder this one. Yeah, I think this one passing rate is pretty high, because all you need to do is go back to the previous question. I fully understand this solution, and I think you'll be able to get it. There shouldn't be any surprises. I just said there shouldn't be any surprises, but I have a surprise. And that is a surprise. Why? Because I'm getting a little bit more than I should. All right, so we have 12, 13, 1, 12. So this should be at 12. 13, 4, 13, 12. This shall add 9, 13, 8, 10, 12. This add 2. This add 4. 12, 13, 12, 12. Nothing gets added. 13, 13, 13, 13, nothing gets added. Now go column wise. I think I know why. I believe we have to do it here as well. I think this should be std small. I believe. Wait, hold on. Do we really need this? Because we're gonna hit them no matter what, right? Yeah, I don't really think we need this though. I think when we go through the first, eventually you will always shift to the other position, and then we'll always run it. Anyway, so if we run column wise, this one is no go because this is 0 already. So you run this 13, 13. So you run here. This will be plus 9. This will be plus 5, but I'll remain plus 4. And now I run here. Right, so this one becomes 0. So we run here, so yeah, that's that. So this one will be gone. This will be plus 3, but now we're plus 2. This will be plus 1, but original is 0, so that's 0. So it should be 9, 4, 2. 15. Okay, that was the original solution, but I think we are saying this is not correct. Huh. So it should be 14. If you look at this, we have 13, 13, 13. It's pretty high on the 3 sides. So this will have 9 above it. And on this side, this is 10. And this is 8. Because from this perspective, if we look down, tallest is 13, right? However, everything's connected. So tallest is not 13. Tallest is 12. Well, it was 13 here. That's what I think is happening. Actually, I'm not quite sure what is happening here. I'm not sure what's happening here. Yeah, so it's only 8, right? If it's only 8, so we can definitely hold 4, right? But the extra 5, depending on its surroundings, because the water can leak through this side, this side, this side, and this side. Right? Water can definitely leak through these sides. Because you need all of them to find how much you can hold. Now, on this side, you do have plus 9, but on this side, you actually have plus 8, plus 9, plus 9, plus 9. This side is plus 4, right? This side is plus 4, and this side is plus 6. So are we saying that essentially for this one, what are we doing here? What are we doing here? But yeah, essentially, if you want to see how much this cell can hold, so you have this cell here, like these are not enough, right? To hold, you have these 4. No, it is enough. Why do you need to consider this? It's sealed in. It's only when this side is smaller, right? If you have this side is smaller, and then how much you can hold in this is dependent on the neighboring. Okay, it's not as simple. Like in this case, yes, because this is only 8. So this cannot really hold 9. Because this 9 is depending on this is 13. Right? That's why I say it can hold 9. But if you look, like the maximum is 13, 13, 13, right? But the maximum going this way is only 12. Maximum going this way is also 12. Okay, what are we doing? What are we doing? What is the height that we're looking for? To know how much water can be held in one position, what I need to know is the maximum height in 4 directions. 4 directions. So for this position, for this one, going up, I have 13. Left is 13, right is also 13. But coming from bottom, and it cannot just go from this direction. I think it's probably is everything. But it's also not really everything. Right? Because you have something really tall, it doesn't really matter. What I need is to know, like if this one is not really that high, because I look at this is 8, right? And 8 is not right. And we have to look around. Because if that's 8 and this is 10, if you add water here, it will spill to this one. Yeah, because it couldn't hold that much. Yeah, we're going to say like in this general region, the tallest is only 12. So like the wall here at highest is only 12. Oh. So if the highest is only 12, yeah, the extra one will flow out, right? It will flow out. Because I say a plus 9, yeah, I think this is not plus 9. This is definitely not plus 9. Because if you plus 9, then you have an extra one. Plus 9 is based on this 13, right? So you have the extra one, it will flow to this cell, right? Because it cannot hold. And that will flow to this cell, it cannot hold. And that will flow to this cell, it cannot hold. And that will escape. Right? You can find a path for it to escape. So what are you saying? Like we go row by row and we get a general idea of how much each can hold, and then we need to what? Like a BFS to see if, or a DFS to see if it can escape? That seems stupid. Right? That seems stupid. I mean, basically, what we're saying is for a cell, I need to see if there is a path, right? I need to find a path that can tell me the lowest, the, oh, the lowest, the lowest cell that is bigger. The lowest that is bigger than the current cell, right? But I need to know the lowest that is bigger. Mm, hold on. Let me think again. Because I go rows already, so I know. Like from a row perspective, but when you do rows, the premises is the all the other rows are like very high, right? So you don't have to worry about the other one. But now the other one is lower, so you have to worry about them, and then you have to worry about them a lot. And what we want to know is column wise. So yeah, it's not just this column. It's not just this column because you're also getting hit here. Hmm. You have a cell and you have another cell because they're all higher than you, right? Yeah, because column wise, or maybe we should do. But if you get the minimum, then this is still 13. Right? It won't help you. Now this turns into something ugly right now. This is something ugly right now. Yeah, I thought go two directions is enough. But two directions is not enough. All right, I need, let's say, oh my god, they don't even have any hints? Come on. Oh, God. What is this? What is this? I think it's more complicated than I had expected. I thought 2 rounds of the original solution would be enough. No way. If it's BFS and it's heap, is this Dijkstra again? Are you kidding me? Really? Okay, so maybe I was approaching it the wrong way then. I was thinking maybe it's just an extension of the original trapping water. Maybe it's not the original trapping water. It's just something more. I mean, it is a graph, okay, and maybe we can see. Yeah, I think the answer for this problem is like this is not 9, right? This is 8, because if you look at the one surrounding it, it's 12, right? It's 12. That's the maximum. But what we want to know, so basically, okay, get onto this. Basically, starting from a cell, we want to walk around, right? We want to walk around to find the not really smallest, to find the largest yes, we'll find the largest number, okay, that's on the border. Now the smallest number that's larger than the target number from the border. From the border. So I go up, right? And then hold on. So I am here, okay? I'm here. So I have 4 that's kind of box me in, right? And if I go this direction, what I need to know is the entirety above me, right? Entirety above me. I want to know what is the smallest height. Like if I have a path from here, can go to the edge such that everything is either equal or smaller than me, then this cell basically cannot hold any water. It cannot hold any water, right? If I have this path. So that's what I want. Like in this case, I go up and I basically cannot go up. Yeah, it's like this entire path towards some edge if everybody is smaller than you. But in this case, I cannot, right? I go here and this is bigger than me. But you can't just say, okay, this is bigger than me, then that's it, right? Because if you go down, you can say, okay, 8 is bigger than me, but that's only plus 4. But you can keep going. It's the minimum height. Like it for 4, we're looking for the minimum height in this region. Not minimum height. Oh my god, what how am I supposed to explain this? It's not really the minimum height. It's so starting from outside, okay, and then coming in. This is the right max, right? Right max coming in to this position is 12. Right max coming into this position is a 12. Right max coming into this position is 13. Right max coming to this position is 13. Uh-huh. But these left max and the right max, they matter, right? They matter. So instead of getting it from the vertical, there's row max, what we need is each max. So basically here is 12, this is 12, right? Just like coming here, right max is 12, left max is 13, right? Right max is, well, this is actually 13 because coming here, so left and right, left max, right max, and a current. So this kind of tell me if I flow down, right? If I flow down, oh, and this is 13, so this will get blocked. Or this is 13 because I have 9 from just a row. This is the maximum that I can get, right? So if you go row, you get the maximum you can get, and then you're asking, can I really get this much? So I try to, so I go the other way. I go column to see if I can really have this much, right? And how do I do that? I ask if for each row, for the different levels, right? Different rows. What is, like for the current row, I say I can get 9, but for the row above me, will 9 be allowed? Now, how do I know if it can be allowed? I get the left max, I get a right max that come into here, but if this is 13, because it's bigger, So it will be the smaller of the left and right max, right? And will be the bigger of this. So this is 13. So allow. So that's good. This one I don't have to go. So I'm now looking at this row. So looking at this row, left max is 13, right max is 12. So and this one is 8. It's only 8. So if you look at this perspective, it's okay. Actually, one of them can get down to here. No, I can't. I cannot. So I just get the left max 13, which means if you look to the left, you have a 13 to stop you. You look to the right, you have 12 to stop you, and you look at the middle, it's an 8. Okay, it's an 8, and you're saying you can hold 9, but in this case, left, right, you need to pick a minimum. So I say, okay, pick minimum, it's going to be 12, right? And this is 8. Which means, so I can hold, by this alone, I can hold 4. So I have 5 extra, right? I have 5 extra. And for 8, and here it's only plus 4, right? Because it's only plus 4 here. It's plus 4, which means when you're coming down, so for this one is plus 4, and I'm going here, right? And this is plus 9. But this is plus 4, which means for this position, and most you can hold is 4. So for this position, it affects this position. So it means for this position, the most you can hold so you're gonna look at this to see what's the water they can hold. And the most water you can hold is 12. And you are 13. So this must not be higher than this. So you have to reduce this to 12. What do you mean? So when you look down, you have to also compare oh, no idea. I guess I have to stop right here and clear my mind again. Let's see. I feel like it's getting close because we already realized that the reason we cannot hold 9 here is because this one at most allow 12. Right, so at each level I know what's the maximum allowed. Right, what is the maximum allowed? So when you go down, when you go vertical, what you can try to see is the highest level that each one at this position is allowed horizontally, right? Horizontally, each one, the max each one is allowed horizontally. So when you go vertical on the same column, right, on the same column, so you should find the minimum that's allowed, which means you should not do water. Okay, let's do one more. Okay, one more. If this one fails, then we don't do it today. So instead of doing water height, I do L max, because this is the maximum I can reach, the maximum height I can reach, right? And I do right max. This is the maximum I can reach. Max height of water. Max height I can reach. Max height reachable with water for each cell. And then we go vertical, right? And then so basically this will be 13, this will be 12, right? And then you go vertical, if vertical wise you can hold more water, but horizontal is already less, so you just do horizontal, right? You will do horizontal. If vertical can hold less water, how do you know vertical can hold less water? You run the same thing. You run the same scheme, and you do one more round. You do one more round. You just go roll the height, because at the end of the day, it shall be the minimum. Because you basically you add water to it, right? You add water to it based on what the horizontal is, and you do vertical, and at the end you shall shave it, right? You shall shave it. What do you mean by shave? You go through everything. So okay, so I do that, and I do that. Go vertical, and then go through water to find a minimum. So we go row to find minimum height. So we'll go row by row to find the minimum. We find the overall minimum. Mean water height. Okay, so I got mean water height. Now we go through everything. I got a mean water height. Then we shall get the height map. So it should be mean water height. If R is smaller than mean water height, plus equal to R mean water height minus R. Alright, so this one doesn't work. We'll call it for today. And we'll see if we have anything else. Nope. I ain't right. Because I think water IJ can be 0. That's the thing. No, it shouldn't be. Oh, press the wrong button. One. How is this 1? Oh, I think it should be T max, right? Should be B max. All right, I need to do it tomorrow. See you guys tomorrow. Adios.